Hi, my name is Emiliano from the Facultad de Química of the Universidad Nacional Autónoma de México. Today I will be presenting you a video about what determines the stability of a carbocation. I hope you enjoy.
In essence, a carbocation is a positively charged carbon atom that has only 3 bonds and an empty p orbital. They can be classified as primary, secondary, or tertiary, depending on the number of carbon groups attached to the positively charged carbon atom. Due to their electron-deficient nature, carbocations are highly reactive and can participate in various chemical reactions, such as nucleophilic attacks and rearrangements. They are also important intermediates in many organic reactions and play a significant role in organic synthesis. Today, we're going to discuss the mechanics of how carbocations work in order to increase their stability. A carbocation can be stabilized in several ways to minimize its high reactivity. The first way is by resonance. A carbocation can resonate between different structures, where the positive charge is distributed in a more effective way. This resonance allows the positive charge to be spread among the adjacent atoms, decreasing the localized charge in a single carbon atom, thus increasing stability. An example can be seen in the allylic carbocation of the 2-propenyl cation molecule. As you can see, the positive charge can resonate between the two adjacent carbon atoms through the movement of p electrons, increasing the stability of the carbocation. Then we have the inductive effect. A carbocation can be stabilized by the influence of alkyl groups or substituted alkyl groups that donate electrons through the inductive effect. These alkyl groups push electrons to the positively charged carbon atom, thus decreasing the localized charge and bringing stability to the carbocation. An example of this effect occurs in the ethyl carbocation, in which the positively charged carbon atom attracts the electronic density from the adjacent hydrogens through sigma bonds, creating a polarizing effect. This withdrawal of electronic density reduces the positive charge on the carbocation, increasing its stability. Hyperconjugation is also a way in which carbocations can be more stable. This effect occurs when there is an interaction between an empty p orbital of the positively charged carbon atom and the sigma bonding or anti-bonding orbitals of the adjacent carbon-carbon or carbon-hydrogen bond. This interaction allows the electron from these bonds to be donated into the empty p orbital, delocalizing the positive charge and generating stability. An example of this effect happens in the isopropyl carbocation, where the adjacent carbon-hydrogen sigma bonds contribute to the stability of the molecule by allowing the overlap of the electrons with an empty p orbital of the carbocation, delocalizing the positive charge. As I said in the beginning of the video, carbocations can be classified as primary, secondary, or tertiary, depending on the number of carbon groups attached to the positively charged carbon atom. This can tell us a lot about the stability present in our carbocation. If you have the basic knowledge of organic chemistry and reaction mechanisms, you may have heard that the most substituted carbocation will be the most stable one. And the explanation of this is a sort of a teamwork among the methods I described before. Primarily, this phenomenon is justified by hyperconjugation. The more adjacent carbon atoms there are in a substituted carbocation, the more hyperconjugative structures can be formed, producing a more p orbital overlaps, increasing considerably the stability of the carbocation. Nevertheless, resonance and the inductive effect, in that order, also contribute to how this substituted carbocation increases stability. For example, considering a tertiary carbocation, the positive charge can be distributed through resonance over these adjacent carbon atoms, resulting in a more stable system. The role of the inductive effect takes place because the alkyl groups, being less electronegative than carbon, donate electronic density towards the carbocation through sigma bonds. This electronic donation helps stabilize the positive charge by reducing the overall charge density on the carbocation. By combining the teamwork of these mechanisms, they delocalize the positive charge and distribute electron density across adjacent atoms, reducing the energy of the system, producing a highly substituted carbocation to achieve generally greater stability compared to a less substituted carbocation. Understanding carbocation stability is crucial in organic chemistry for several reasons. It allows us to predict reaction mechanisms, determine reactivity patterns, design efficient synthetic routes, optimize drug design, and build a solid foundation for studying organic chemistry. Carbocation stability considerations are essential for rationalizing and controlling reactions, predicting products, and advancing our knowledge of chemical reactivity. This knowledge finds application in diverse areas, including pharmaceutical, research, synthesis, and medicinal chemistry. Overall, learning about the carbocation stability is fundamental for understanding and manipulating organic molecules and their reactions.